안녕하십니까. OSC코리아에서 비즈니스 석세스를 담당하고 있는 장수영 이사입니다. 오늘 오픈테크넷서밋 버추얼 컨퍼런스 2020에 초대해 주셔서 대단히 감사합니다. 오늘 저희 파트너사인 인스타나와 함께 마이크로 서비스 환경의 어플리케이션 모니터링 싹쓸이라는 주제를 준비해 보았고요. 진행 순서는 OSC코리아 소개를 좀 먼저 짧게 드리고 미국 본사의 엔지니어를 모시고 인스타나를 이용하여 클라우드 환경에서 어플리케이션 모니터링 하는 것에 대한 소개를 드리고 또 간단한 데모도 보여드리겠습니다. 클라우드 환경에서 어플리케이션 모니터링에 대한 소개를 드리기에 앞서 저희 회사를 먼저 간단히 소개해 드리려고 합니다. OSC코리아는 OSC 아시아 그룹 소속이고요. 오픈소스, 보안, 컨텐츠 중심의 비즈니스 플랫폼을 운영하고 있습니다. 최근에는 클라우드 네이티브 MSA 서비스를 제공하는 디지털 트랜스포메이션 전문 기업으로 발돋움하려고 노력을 하고 있습니다. 저희 주요 사업 영역을 좀 먼저 간단히 소개를 해드릴게요. 저희는 말씀드린 대로 오픈소스의 O, 보안, 시큐리티의 S, 그리고 컨텐츠 중심에서 컨텐츠 C라는 이 세 글자를 중심으로 솔루션 인큐베이션을 하는 비즈니스 플랫폼을 운영하고 있습니다. 그래서 저희가 인큐베이션 하는 솔루션들은 대부분 클라우드 네이티브 환경이나 마이크로 서비스 아키텍처에서 많이 사용하는 그런 솔루션들입니다. 대표적으로 오늘 소개해드릴 어플리케이션 모니터링 솔루션 인스타나가 있고요. 그 이외에도 클라우드 클러스터 플랫폼인 렌처, 기업형 이벤트 스트리밍을 위한 카프카 컨플런트, 또 클라우드 시스템의 장애 테스트를 위해서 카오스 엔지니어링이라는 기법을 도입한 솔루션 그램린 등이 저희의 주요 솔루션들이고요. 클라우드 네이티브 환경에 맞는 포트폴리오를 구성을 해서 가급적이면 고객사들이 필요로 하시는 디지털 전환이나 클라우드 전환하는 데 필요한 솔루션들을 제공을 하고 있습니다. 또 저희의 두 번째 상업 영역 중에 하나가 클라우드 컨설팅과 프로페셔널 서비스를 제공을 하고 있는데요. 마이크로 서비스 아키텍처, 클라우드 네이티브 환경으로 전환하는 고객사가 요새 많이 문의를 주고 계신데 저희가 클라우드 전환에 대한 컨설팅이나 구축, 또 이런 지원 컨설팅, 그리고 구축 이후에 운영 유지 보수까지 지원을 해드리고 있습니다. 저희가 주로 하는 역할은 테크니컬 아키텍트나 어플리케이션 아키텍트, 솔루션 아키텍트 등 아키텍처 그룹을 만들어서 고객사가 필요로 하는 부분들에 지원을 해드리고 있습니다. 또 저희가 마이크로 서비스 컨설팅을 시작한 지는 그렇게 오래되지는 않았는데요. 짧은 기간 동안에 저희가 그래도 많은 성과를 좀 이뤘습니다. KT, 포스코, 한진그룹, 신세계, 현대자동차 등 좀 국내에서는 큰 기업들과 함께 많은 프로젝트들을 했고 저희가 자부하는 바는 아마 국내에서는 MSA 프로젝트를 가장 많이 한 기업 중에 하나가 아닐까 생각하고 있습니다. 저희 주요 고객사는 조금 전에 말씀을 드렸고 이런 코로나로 인해서 아마 여러 가지가 바뀌고 있고 아마 이번 서밋도 그래서 이번에 버추얼로 진행이 됐는데 그러다 보니 언택트 얘기가 계속 나오고 있고 이런 언택트는 결국은 저희는 클라우드로의 전환이 더욱더 가속화되고 있다고 생각을 합니다. 그래서 최근에 저희도 이렇게 많은 고객사들로부터 클라우드를 도입하고 또는 기존에 사용하시던 클라우드를 확장하거나 효율화하기 위한 마이크로 서비스 아키텍처 도입에 대한 문의가 늘고 있고요. 컨설팅을 이렇게 해드리다 보면 서비스 도입 전에 대한 부분도 고민이 많으시지만 서비스가 다 도입이 되고 난 후에 그 프로덕션 스테이지에 대한 모니터링 부분도 문의를 굉장히 많이 주세요. 그래서 이런 부분들을 해결할 수 있는 솔루션인 인스타나를 오늘 좀 설명을 드리려고 하고 있고요. 인스타나는 이미 글로벌에서는 그 기능과 성능이 검증이 된 어플리케이션 모니터링이고 국내에서도 이미 메이저 이커머스 기업에서 도입해서 사용 중인 솔루션입니다. 이제 저희 회사 소개는 여기서 좀 간단히 마치고요. 인스타나를 소개해 주실 인스타나의 시니어 솔루션 아키텍트 드루 플라워즈를 소개합니다. 세션은 전부 영어로 이루어지기는 하지만 자막을 제공해 드리니 즐겁게 경청해 주시면 감사하겠습니다. 감사합니다.
So, You've decided to think about microservices. Perhaps you have a big monolithic code base and you're looking for a way to improve performance, flexibility, and scalability of your system. It seems simple, right? Just take your existing code and turn it into individual services performing specific functions. But once your system transitions from a traditional app server and database architecture to something that looks more like this, a question begins to arise. How in the world do you monitor this thing and find performance impacting problems? My name is Drew Flowers, Solution Architect here at Instana. Today I'd like to show you how we at Instana solve this problem. But before I do, can I get a little help explaining the fundamentals of microservice observability from my colleague, Senior Software Engineer Fabian Staber, and a talk he gave at DockerCon 2020 on monitoring in a microservice world.
Let's start with metrics. So metrics are actually very easy to understand. Metrics are time series data. So you see an example in the top right of the slide. You have the x-axis, which represents the time. You have the y-axis representing the value. And a metric is basically a value changing over time. So the value is going up and down. And those metrics are actually well better suited to describing the application state than simple health check results. To give you an example, a typical metric that you often see in monitoring is latency, right? For a specific HTTP endpoint, you want to know how fast does it respond, right? And then you can use this metric information and define service level objectives with it. You can, for example, define that for my specific HTTP endpoint, I want that 95% of the calls are responded faster than 100 milliseconds, and only 5% of my calls may be slower than 100 milliseconds, right? That would be a good definition of a healthy application state, and this is a definition that plays well with highly distributed applications, right? And if you have this type of definition, this type of server level objectives that you can use to define what does it mean for your application to be healthy, then you can use this as a basis for defining your alerts. You can say, if my service level objective has been violated for, say, at least 5 minutes, then I want to be alerted. I mean, if for 5 minutes, more than 5% of my calls were slower than 100 milliseconds, then something is seriously going wrong and I want to be alerted about that. So that's the type of way you define alerts for modern distributed applications. And an interesting aspect about these metrics and metric-based alerting is that those metrics are in many cases easy to understand and easy to use, right? You see your latency metric and you know what it means. But if you look under the hood, what it actually means to provide that data, like the work that's taken by your monitoring system, it's surprisingly subtle and complex, right? And the things that make it complex is, first of all, if you want to have the latency of a specific HTTP endpoint and you have a system that dynamically scales out, you know, if load is high, it starts more instances of your particular service. Then if you want to know the overall latency of your endpoint, the monitoring system needs to aggregate the latencies of the individual instances providing this endpoint, right? And this, of course, this horizontal aggregation that changes over time as services scale out or scale back again. But apart from this horizontal aggregation, there are also vertical relationships. And with vertical, I mean that imagine your service level objective is violated, like at a given point in time, say more than 5% of your calls take longer than 100 milliseconds to respond. And what do? You basically want to look at your metrics and related metrics and try to figure out what happened. And so you maybe first you see that your service is a Java deployment in a servlet container, right? And then you see, okay, it's responding slow for some reason. What you want to do is you want to drill down the system stack. You want to see okay, this Java deployment is running in a servlet container, so let's look at the servlet containers metric. This is running in a JVM, so let's look at the JVM metric, like garbage collecting activity, right? The JVM is running in a Docker container, so let's look at the Docker containers metrics. Or this Docker container is running on a physical Kubernetes node, so let's look at the node metrics. And maybe somewhere down the stack on the physical layer you see, oh, this one has, I know, disk I/O that's total overload, and maybe this disk I/O is related with why the service responds so slowly. And so you have both dimensions. You have this vertical dimension and the horizontal dimension, and both dimensions change over time. The horizontal dimension changes when services scale out and back again. The vertical dimension also changes because your Docker runtime platform might at one point decide to kill your Docker image, kill your Docker container, and schedule it again on another physical host, and then you still have the same image providing the same service running in your cluster, but the underlying association with the hardware changed. It's all of a sudden running on a different node, right? And this is, you know, if you want to use your metric to do root cause analysis or to have these aggregations and to see what's going on, then basically the underlying monitoring system needs to take care of all these relationships. And there are different ways how different monitoring systems solve these. What we, for example, do at Instana is we actually explicitly model those relations in something that we call a dynamic graph. And this dynamic graph has all the relations and it changes over time. So you can basically scroll back to any given point in time, look at the horizontal dimension, look at the vertical dimension, and relate all different types of metrics that we collected at this point in time with the configuration as it was at that point in time. Good. So that was a quick introduction to metrics. So basically, metrics are time series data and are a good way for defining what it means for your application to be in a healthy state. The other type of data that is often used or more and more used in monitoring are distributed traces. So distributed traces are about understanding the distributed system behavior, right? You have a call coming in to a service A, this service A calls service B, this service B calls service C, etc. And you want to know which services are involved with actually responding to that incoming call. And the way distributed tracing works is initially, when a new call is generated, a unique identifier, a random identifier is generated, which is called a trace ID. And whenever one service triggers a call to another service, be it synchronously or asynchronously within the context of resolving a specific call, then the trace ID is also passed on to the next service. How is this done? Depending on the protocol, of course. In many cases, services communicate with each other over HTTP, and then obviously the trace ID is passed on as an additional HTTP header, but of course other communication protocols have their own means of attaching metadata as well. For example, if you have message queues, you can use message queue metadata to transport the trace ID. Right, and then every individual service, of course knows how long it took to respond the incoming call, which outgoing calls were triggered, how long it took to respond the outgoing calls. And the monitoring systems collect all this information together with the associated trace IDs. And then in the backend, we can bring all this information together and create a distributed call graph describing the distributed system behavior. You see an example representation of a trace in the bottom right corner of the slide. So what you see here is we have the long blue line, which is the initial GET request going into a system. And then the first thing that happens is the orange stuff where the system triggers a database request, and then a millisecond passes where it obviously processes the result, and then a new GET request is fired to another service, and this other service has again such an orange bar indicating a database request, and so on. So you can, I think you get the picture. You understand which service triggers which other service for resolving a call. And this is key for understanding your distributed systems behavior. If you enable your engineering teams to ship new services into production, if you have a dynamic changing environment, you will not have, your big PDF document describing all the relationships of the different services. But at some point in time, you need to understand what's happening, and traces are a good way to give you the real picture, to show you what's actually happening in your distributed system. And of course, this data is totally necessary for root cause analysis. For example, if a service responds HTTP 500 internal server error, if you have tracing enabled, you can navigate to the trace of this call that produced this error and then drill it down. And then you see, okay, this service called another service that responded HTTP 500, and this service tried to access a database, and there was no database connection available, and this is what failed, right? If you have those errors, happening a few levels down the distributed call stack, this is virtually impossible to figure out if you do not have tracing in place. But if you have tracing and can just click on an example call and see everything that happens, it's very easy. You see immediately where the actual error happened and where to look and what to look at to fix the error. So, what are the things to watch out for? What are the things happening under the hood that make tracing maybe a little bit more complicated than it looks? I mean, the first thing that's really important is if you want to use tracing, you should find a way to have tracing enabled for all of your services, right? If you are running a mix of some legacy services and some new services, and you end up with a scenario where the new services have tracing enabled and the legacy services don't, then your traces will be rather useless, right? Because there are gaps whenever a call is happening to the old world, and you will never get the real picture, right? And so in order to have everything instrumented with tracing, you should have a monitoring system that allows you to instrument legacy services with tracing at runtime, right? There are different ways how to do this. Like, for example, in Java, typically those systems have Java agents that you can attach to the running process and that then instrument your service with tracing, and all of a sudden your legacy service provides tracing data. And of course, monitoring products kind of support all different types of programming languages, frameworks and stuff, so they can really attach to a lot of things, and chances are good that everything you have actually running in production is supported, and then you have a total coverage for tracing across all your service landscape, right? So avoid gaps. Try to find a way to instrument everything with tracing. And then, of course, as your landscape is more complex and has maybe a lot of services involved with monitoring, then grouping becomes important, right? I mean, for some people who really want to understand what's happening within a cluster, it might be good to have the full picture and to see everything. Maybe for other people who just, treat your services as a black box, it would be good to say, I'm only interested in ingress and egress, only in incoming and outgoing calls, but I'm not interested in what happens in the actual cluster. And so I want to, group that together and treat it as a single service, although it under the hood is implemented as a collection of multiple services. So, but that's kind of, if your environment becomes more complex and you want ways to structure things. Good. So distributed tracing allows you to understand the distributed system behavior, which services are involved when responding to a request.
Now that we know the basics of microservice observability, let's talk about practical solutions to this problem. There are many tools out there to help you monitor your application. But seeing as how I work for Instana, today we're going to focus on our approach and what makes it special. At Instana, our goal is to provide full stack monitoring that takes never sampled automatic distributed traces, correlates that activity to end-user monitoring traces, looking at both website and mobile applications, and contextualizes this with high-fidelity time series metrics, looking at platforms, which we define as Kubernetes, Tanzu, formerly Pivotal Cloud Foundry, and VMware ESXi, as well as the underlying host-based infrastructure everything is running on top of. We provide this data through our intelligent, unified agent that can be easily installed on any platform, whether it be Kubernetes, serverless systems like AWS Lambda or Fargate, or even more traditional Linux or Windows-based virtual machines. The Instana agent is designed to detect and configure itself to monitor 250 technologies out of the box, with all detected entities displayed on each host. Once the configuration process is complete, we begin streaming metrics for every component to our backend every single second, giving you near real-time visibility into your infrastructure's operation. We pair this with a contextual understanding of your environment powered by a tool we call Context Guide. Context Guide allows users to understand exactly what the asset they're viewing is from an infrastructure, platform, and application context, so there's never any question what application, cluster, or host this component belongs to. In a microservice world, it's likely you'll have some kind of platform providing orchestration, so we need to ensure those are operational and the metrics we care about are being collected. Instana not only collects the platform metrics out of Kubernetes, but also the orchestration events, along with a host of other details. Like our pod map, which can visualize your CPU and memory limits and requests, or how many containers are being spawned per namespace. And if you happen to be using Tanzu, formerly Pivotal Cloud Foundry, we also collect details on the Diego cells to go along with the data already provided about the VMs in the foundation. When it comes to what makes Instana truly special, it's all about our never-sampled distributed tracing and analytical capabilities powered by application perspectives. App Perspectives allows for a deep understanding of the application's performance, aggregating for those golden KPIs, throughput, error rate, and latency, as well as automatically tracking all application dependencies. Setting up an app perspective is as simple as telling us what kind of application or situation you would like to model, and our automation will take care of the rest, resulting in a curated dashboard giving users the ability to drill down through their application with extreme ease, going from the top end all the way down to an endpoint. App Perspectives is paired with our unbounded analytics, which allows you to utilize simple drop-downs to generate queries and hunt for high latency requests and assess any trends that may relate to throughput, latency, or error rate. Unbounded Analytics also houses our production-grade code profiler, which takes profile snapshots every 2 minutes and then aggregates that data to show you how your methods are leveraging CPU, memory, or system wait time, allowing operators to know with precision where they should spend their time optimizing their code. As Fabian said earlier, both metrics and traces are key to understanding microservice performance. However, it's not always about how the backend behaves. Your customers are what really count, and to ensure they're happy, we provide end-user monitoring with all Instana agents. The Instana EUM can monitor both websites as well as Android or iOS applications. Once deployed, you get all of the data you would expect, from page loads and transitions to navigation and paint timing, as well as JavaScript errors. But that's not all. With smart alerts, you can provide yourself actionable insight by baselining and monitoring user experience and providing dynamic thresholds based on your application's traffic. We can also do something pretty special. Through a combination of our end-user monitoring and our never-sampled backend traces, we can show you a complete user journey, tracking pulled resources and metrics from the user's browser and automatically correlating it to the relevant backend trace with the push of a button. When microservices break, trying to diagnose the failure can be one of the most painful tasks for an engineer. Due to the complexity of so many potential services compounded by orchestration, assessing the root cause can rapidly turn into an exercise in futility. For this reason, Instana has an intelligent alerting system designed to help you reach root cause as quickly as possible. It starts with over 230 out-of-the-box alerts that are categorized into 3 event types. First, you have a change. This can be something as low-level as container labels changing to processes or hosts spinning up and down. Next, we have an issue. Low-level items like CPU load spiking or memory becoming exhausted. Finally, there are incidents. Incidents are where our machine learning is telling you the application is experiencing significant impact. When these occur, we also want to assess what other application services or infrastructure entities are failing and provide you this. Here we have 21 events on 7 different application entities, all tied to one problem. Here is our first failure, our front end experiencing an increase in latency and errors. As we follow the timeline up, we can see all the other services that are also currently having a problem, all of which is related to this failing SQL database here at the top. We even call out that this was an abnormal process termination. So rather than giving you 21 individual alerts, Instana gave you one and contextualized the scope of the problem. Monitoring microservices is hard. Without proper observability, it can feel like driving through a city blindfolded. But with the right combination of tools, bringing order to chaos is not out of reach. If you're interested to learn more about how we at Instana tackle this challenge, please visit play-with.instana.io. And from everyone on the Instana team, thank you for your time today.